Welcome to the presentation on database encryption by Group 38, Yotaro, Shinjo, and Chang. Since this is a big topic, we decided to focus on two important aspects, encryption method and key management. We are restricting our scope to relational database only, and here is a little reminder in case you forget what a relational database looks like. Each row is a complete record, and each record consists of several field or column values. Encryption can be done at different levels, but we are only focusing on the database management system level, where some of our familiar cryptographic ideas, such as Chinese remainder theorem and RSA, play an important role in the design of encryption. The idea of granularity will also become obvious once we see an example. The first encryption method is based on Chinese remainder theorem. The idea is to have unique encryption and decryption keys for each field. We encrypt a record as a whole and retrieve different field values using different decryption keys. The system naturally supports access control. I can give user read access to only some fields by giving him the corresponding decryption keys. I can also give a user write access by giving him all the encryption keys. Note that the X value that's concatenated with the field values is a hash value. It can be used to check the integrity of data. We know there is a unique solution C to the system of congruences if D values are pairwise coprime. Suppose F values are field values, the actual data we'd like to protect, and D values are decryption keys for corresponding fields. We can construct encryption keys by multiplying big N and M. We also need a big D, which is the product of all small d values. The encryption and decryption processes are shown at the bottom. The record is encrypted into just one value, but I can use only one decryption key, which is D1 in this case, to retrieve the value in field 1 separately. It should be obvious that encryption is at row level and decryption is at field or column level. The scheme also supports access control and integrity check, but most importantly, is it safe? Well, brute force is hard because attacker needs to guess all the decryption keys. However, there is the situation where if I give a user read access to all fields, he will have all the decryption keys and he can compute all the encryption keys himself and grants himself write access. And this is definitely a safety threat. What's the performance overhead? Assuming n is the number of fields, encryption requires n multiplications, one addition and one modulation. The complexity is O(n), which is not bad. Is it space efficient? Maybe. Although each record is represented by only one value, we only know that this value is smaller than big D, and big D is a product of several numbers, which can be really big. Note that a database encryption, unlike message encryption, needs to have some more capabilities. Its performance overhead needs to be small because data can be rapidly inserted into the database. Space efficiency is also more important because some databases can be gigantic and very costly to store. Using such criteria, we can tell this scheme is a bit immature, but trying to satisfy the criteria has always been the guidance for the development of database encryption.
Most secure systems classify users into a number of security classes or groups, which corresponds to the security level attached to the data. In these systems, write-up, read-down rules are commonly agreed. This means that any user can read and write the data to the database if the data is of the same security classification as the user's security clearance. And a user with lower security clearance can only write data to a higher level or the same security level as the user in the database, which is the write-up. A user with higher security clearance can only read data at the same security or from a lower security level, and this is the read-down. This prevents low clearance users from reading sensitive data of higher security classification and prevents high clearance users from giving higher clearance data to lower clearance users. Within the multi-security level database using RSA encryption, the keys issued to the users are chosen in a multi-level fashion, giving the number of higher clearance users more powerful keys and low clearance users weaker keys. Lower clearance keys can only read same or below level data or request data to be stored as higher level. Any two factors of d of n whose product equals to d of n can be used as key, and we call those parent keys. The scheme gets its multi-level property from the fact that given a pair of parent keys generated using D of n, this key can decrypt encrypted data using some of other parent keys also generated from the same D of n. Let's say D of n has divisors d1 to dn in an increasing order, and the product of each pair, d1 dn, d2 dn-1 and such, are equal to D of n. We have to pick pairs where keys with lower index can be divisible by upper index keys. If we encrypt data using dn-j and dj+1, then we can decrypt using dk, where dk equals alpha times dj+1 for some integer alpha greater than 0. And thus we have the second formulas, where k actual is the actual decryption key used by the security system. So for our data m, we can compute by the third formula. Now we can decrypt lower level cipher using higher security key. However, not the other way around, as lower key cannot figure out alpha in the first formula to get alpha up to tn.
I would like now to discuss key management. Cryptography uses key to encrypt and decrypt data, so keys protection is particularly important in the database protection solution. Keys management is the way keys are generated and managed during the life cycle in crypto system. Let me turn now to describe solutions. The first and easy solution is to store keys in the database. These keys are protected by the master keys, which in turn is stored somewhere in the database server. However, an administrator with access privilege can get these keys and decrypt any data they want without any limitation. To solve this problem, the second approach is introduced by using the hardware security module. Encryption keys are also encrypted by master keys, but now they are stored in the hardware security module. The SSM is trusted because it has a security-focused OS, and its service access is strictly controlled with internal rules through a network interface. Application sends a request to the database server to query data, then the database management system engine will communicate with SSM to get encryption keys. These keys are temporarily stored in the database server RAM. After that, the DBMS engine gets encrypted data from the storage layer, uses key in RAMs to decrypt data, and returns query result to application. The important notice is that keys will be destroyed from the database server RAM as soon as cryptographic operations are completed. Another solution is that SSM is separately deployed in the security server. A new component is added in the DBMS engine named Security Module is responsible for communicating with the security server to get encryption keys. Now we can separate database administrator and security administrator roles in the system. Security server and SSM minimize the encryption keys exposure. However, it does not fully protect us might capture RAM to get encryption keys. The new architecture is proposed by researchers to avoid the exposure of encryption keys during the data query process. The SSM now manages user privilege encryption policies and keys. This approach takes advantage of database level encryption and security server approach, but does not expose encryption keys. Security server is now embedded in SSM. DBMS sends whole encrypted data to SSM. In turn, SSM will decrypt data and send back decrypted data to DBMS engine. The encryption keys are internally managed in SSM, with no exposure outside. An alternative solution is that SSM is deployed in a single client. It only handles data processes for one client, so the embedded code would be similar and requires fewer computation resources.
In conclusion, we conducted survey research on algorithms used for database encryption and its key management. More detailed information and demonstration of Chinese remainder theorem and RSA encryption are introduced in the final paper. Thank you for listening.